Welcome to Excel Business Statistical Analysis video 36. And in this video, we got to talk about sampling. And one of the most amazing things in all of statistics, the sampling distribution of Xbar. Hey, Chapter 7, we got to talk about sampling. And then one of the more amazing things, the sampling distribution, which will be a distribution of all of our Xbars and P-bar too. And we're going to learn about the central limit theorem, which will come from some things we learn when we create a sampling distribution. Now I'm going to go to page 9 in the PDFs. Here's page 9. In chapter 6, we looked at our normal distribution, but we were always talking about X values and probabilities. Not only that, but we had the population mean and the population standard deviation, mu and sigma. And we were talking about X, right? But here's chapter 7. We're going to treat the X bar as a random variable. That means we will plot all of the possible X bars from a given set of population data, and we're going to discover some profound things. The normal distribution, down here our random variable is going to be X bar. Now in chapter 7, we're still going to know the population mean, but we'll learn something quite amazing about that. And we're still going to know sigma, or population standard deviation. But all of our random variable, those are going to be actual samples we take, X bar. And we'll also talk about proportions where we have P bar. Then in next chapter, chapter 8, we'll talk about what to do when you don't know sigma, the population standard deviation. Home to get back to page 1. All right, so sampling and sampling distribution. We're going to start off by talking about sampling. Hey, population, that's all of the data points. Sample, just some of them. We'll talk about one or two methods of actually how to go and pick your sample items. But you get the idea. All the items, some of the items. Now what happens is we have a population mu, our mean of all of these sales values. $289 approximately, right? Well, when we took a sample and calculated mean X bar, we got what's called a point estimate of our population mean, our X bar, 255. Well, what's the difference between these two things? It's called sampling error. And we can see it's $34. Now the question is, what are we going to do with that sampling error? Is the sampling error just sampling error? Hey, we just took a sample, so we're not going to have exactly the same values. Or does it represent a true difference? So is the point estimator good enough? And really what we're going to ask is it reasonable? So in this chapter, we're going to build a model so we can check whether our point estimator, either X bar or P bar, and the sampling error, are those reasonable? Sometimes we're going to take a sample and it won't be reasonable, which means it's not a good point estimator. Other times we're going to take a sample and we'll run our test and it will be reasonable. And we'll say that, yeah, the point estimator is a fair representation for the population parameter. Again, the model that we're going to use here to help us decide whether our point estimate is reasonable is called the sampling distribution. But first, before we talk about the amazing sampling distribution, let's talk about sampling. Page 3 in our PDF, sampling. Hey, why do we take samples in the first place? Well, a few reasons. Some populations are just impossible to check. We can't count all the fish in the sea. And yet, it's very important sometimes for people to do samples to figure out how many fish there are, how many dolphins, how many orcas. Another reason calculating off the population costs a lot. An example from General Mills, they might hire a firm to test a new cereal. The sample might cost $40K. Population, that means going out and asking every single person? No way, way too much money. Another reason that we take samples is contacting whole population is time consuming. Political polls can be conducted in 1 to 2 days, whereas, of course, contacting the whole population would take years. How about destructive nature of some tests? If you're making wine and manufacturing, you cannot test every single bottle of wine. If you make seeds for farmers, you can't go out and test every single one because then there'd be none left. And finally, and most importantly, samples are usually adequate. And a great example is the consumer price index. Those taken from samples are quite accurate. Now, why do we need samples? Hey, we select samples to answer research questions about the population. Here at Highline Community College, do Highline students think advising should be mandatory? That's a question right here on campus they're trying to figure out right now. You know, we could, at Highline, get to every single person because actually we have a list of all the registered students, but it would take a long time and it probably would be impossible to get everybody to answer this question. But sampling, we could get a reasonable estimate of what people thought. For manufacturing, is the machine filling accurately? So if you're filling boxes of cereals or bags of lettuce, we absolutely need to periodically sample to make sure the machine is working. Hey, next question about sampling. If the population is so big, how do we know where to go and get the data? Well, the first thing is we have to be careful. And the big thing we have to be careful of, we must make sure that the sampled population is the same as the target population. Now, sampled population, that's just population from which the sample is drawn. And target population, that's the one we're trying to actually get at. Population we want to make the inference about. Here's an example to illustrate the difference between sampled and target. The goal is to gather data about students at Laney Community College. That's a community college in Oakland, California. And by the way, they have a great culinary arts restaurant there. So here's the deal. If you took a sample from Laney College registration list, the sample population would equal the target population. Because remember, our goal is to gather data about students at Laney College. But if we took a sample from people who ate at the culinary arts restaurant, that means we just went there and it was convenient for us just to ask people as they were eating, right? The problem with that scenario is we would get some students from Laney College. They would be in the target population. But we'd also get some people eating who are not Laney College students. Those people are not in the target population. So in this example, the sampled population would actually be people eating at the culinary arts restaurant, whereas the target population was all the students. So the target population would not equal the sampled population. Some other examples. If we were trying to calculate Seattle house price mean and we accidentally used some data from Burien also. The target population was just Seattle house prices, but we accidentally mixed and got some from Burien also. The most famous example, example 3, and I'll let you Google this because this is quite an amazing one. The 1936 presidential election was between Landon and Roosevelt. And there was a famous poll that was done, and they only used phone directories and other lists that they mistakenly thought represented the whole population, but they only represented middle and upper class people. So the views they got were highly biased. Well, this famous poll disastrously mispredicted the outcome. And of course, Roosevelt won. Here, the sampled population was the middle upper class instead of what they really wanted, the target population, which was lower, middle, upper, and everything else, all the classes together. All right, now we got to talk about what a frame is. And a frame is simple. It's just a list of all the elements in the population, or a list of elements that the sample is selected from. Now, you can imagine that frames are not always possible to create. So example frames that you can create. Well, if we had a list of all the names of registered students at Laney College, that's something we can get or obtain. A list of all the companies listed on the New York Stock Exchange. So if we were going to do a sample, on just some of the companies, we could choose from this list. These are finite lists. If we actually have a list, then we can use what's called simple random sampling. And we'll look at an example of that in Excel. We'll put a list there and randomly select some data from that list. Examples of frames that cannot be constructed. Population is too big, like all the fish in the sea. Actually, there was a famous study just recently, back in 2008, I think it was started, and it went on for years and years trying to actually count all of the fish in the sea. But of course, they were doing a sample. Also, frames that cannot be constructed, populations from an ongoing process. For example, machines filling boxes of cereal, transactions occurring at a bank, customers entering at a store. In all of these cases, it's theoretically infinite because there's no upper limit. We consider it infinite because we cannot construct a frame. Even though customers are entering a store, right, we can count. There's 2 people that just came in. But theoretically, any number of people could have come in at that particular moment. As you can imagine, if you have a frame, then it's a lot easier to randomly select items from a frame than if you don't have a frame. Now, let's scroll down and talk about 2 sampling methods. The first one we're going to talk about is when you have a finite population where you have a frame. We can use simple random sampling. Now, we're going to cover this over in Excel in just a second. But the key is we're going to add a new column and use the rand function to randomly generate a number. And then we're going to sort those random numbers and pick whatever items are at the top. Here's some information about rand. We'll talk about that over in Excel. Now, the second method for sampling is for infinite population or an ongoing process. It's called random sample. Now, we're going to select any n units in a random way. But 2 things must be true. Each element must be from the same population. Sample population has to equal target population. Now, for an ongoing process, people walking in, or an infinite population, remember, we don't have that frame, that list. If we look up here for simple random sample, we're actually going to have the frame sitting right there. So that's all of the items that are sampled and the target. But down here, if it's infinite or ongoing process, we have to be really careful that the sampled population is equal to the target population. The second thing that must be true is each element is selected independently. This is so we don't have bias. We don't want to select all the items from a similar group, similar attitudes. Now, if you imagine you were polling people walking into a restaurant. Well, if you only ask people of a certain age group because you felt comfortable talking to them, that would mean you are not selecting sample elements independently. There is a bias. So both of these things have to be true when you do a random sample. Now, when you're doing an ongoing process like filling a machine, to make sure that each element is from the same population, you choose samples from the same point in time. So all elements for the same population. So you make sure that you pull all the bags of lettuce or all the bottles of ketchup or whatever, and right at that one point in time, and then weigh them, sample them, etc. Now, I want to go over to Excel and figure out how to do a simple random sample. Here's the method that we're going to use, but I want to investigate a little bit before we actually do the actual random sample. And I want to look at the definition of simple random sample. The definition is a simple random sample of size n from a finite population of size n is a sample selected such that each possible sample size of n has the same probability of being selected. Now, before we can really make sense of this, I actually want to try and list every single sample and see what they're talking about. So let's go over to Excel. Now, before we list all the possible samples, let's just look at one sample. Here's our original data set that we started off this video with, sales rep and sales. And here's one possible sample. There's the names. There's the values. Now we have a population side big N of 7. 1, 2, 3, 4, 5, 6, 7. The population mean or mu is 289. We just took an average. Population standard deviation is about 74. Now here's our sample. sample mean equals X bar equals the point estimator of the population mean. So here we come over and we calculate our mean using the average function. When I hit enter, 255. That's the point estimator of our population mean. But we can see that there's a big difference. And the difference is called sampling error. We're going to take X bar and subtract our population mean. Enter. So our point estimator is $34 below the population mean. Now, part of what we'll do in this chapter is we'll find out if our point estimator and the sample error seem reasonable or not. Is this sample error too big, or is it okay? It's just sampling error, and we'll accept this as a reasonable point estimator to the population mean. Now, this is just one sample. Let's go over to the sheet, all possible samples. And no way, here's our data set. We're going to try and list every single sample. Now, we actually did this earlier in the class where we looked at big N, population 7, sample size 3. We used the combination function to calculate how many total samples there would be. I got busy listing every single one. Joe and Sue, I listed those 5 times, and then I listed all the matches. Oh, and I went through and did it over and over for every single possible sample. Now, the one we just did on this sheet right here, Chin, Kip, Joe, that's in here somewhere. But first, I want to actually get every single number. So this 185 goes here. This 250 goes here. So for Chin, this 210 goes right here. Then I want to calculate every single possible X bar. Now, there's no way I'm going to copy and paste, copy and paste. Instead, we're going to use a lookup function to look up each individual sales rep and return the sales. Now, the function we're going to use is XLOOKUP. The lookup value, that's what we need to look up. So we need to look up Joe, find a match in the sales rep column. That would be the first row, and then return the sales. So in lookup value, we need to put every lookup value. Control-Shift down arrow. So right now, XLOOKUP has a bunch of lookup values, comma. The lookup array, that's where XLOOKUP is going to try to make a match, comma. Return array, this is what to return to the cell. Because XLOOKUP has many lookup values, when I hit enter, it will simultaneously look up the sales for every sales rep and spill the results. So I come to the end. We don't need any of the remaining arguments. Close parentheses. And when I hit enter, those are all the sales value. Joe, 185, perfect. Tyrone, looks like it's 402, perfect. All the way down to the very last one, Kip at 370. Now we have 3 values for every single possible sample. And now we can calculate X bar. For every single possible sample point, Control Enter, and double click and send it down. Now, if we look through here, and I don't remember who it was, Chin, Kip, Joe. So Joe and Chin, and here it is right here, and there's our sample. But look, that's just one, and there's 34 other possible samples. Now, part of what we're doing here is helping us understand that definition, but also this is going to lead us up to the sampling distribution of Xbar and then the central limit theorem, which will give us real power. Now, let's just go back to our PDF. And notice it says, a simple random sample of size n from a finite population of size n is a sample selected so that each possible sample has the same probability. So here it is. We have every single possible sample. And what's the probability of each one? It's a uniform distribution, 1 divided by 35 possibilities. F4, Control Enter, double click and send it down. So if we're going to do a real simple random sample, the process we use better have 0.0285 for every single one of the possible samples. Again, if we calculate randomly select a sample, it's going to be one of these. All right, well, guess what? There's a built-in function in Excel that follows a uniform distribution, and we're going to use the rand function. Now, the rand function is argumentless. That means you just put open parentheses, close parentheses, and then enter. It randomly generates a number between 1 and 0. It's actually greater than or equal to 0 and less than 1. But it's got a number with 15 digits. And it's random. If you hit the F9 key, which is the evaluate key, it randomly generates numbers between 1 and 0 up to 15 digits. This follows a uniform distribution, and we can use this when selecting our samples to simulate exactly this. Now let's scroll over here. We will come back to this when we build our sampling distribution of Xbar and use this to build the actual distribution. But what we want to see now is how to create a simple random sample. So we'll click on the sheet, Simple Random Sample. Here's our data set. We're going to add a column with the rand function. Then we're going to sort it and then copy and paste the ones on top. Our sample size equals 3. We obviously have a finite population, and here's our frame, right? So we're going to start off with equals rand. Control Enter and copy it down. Now, one thing about the rand function is, watch this. If I start typing over here, watch when I hit Enter. Oh, anything you do at all triggers rand to recalculate. So what we're going to do is now we're going to sort. So I want to click in a single cell. And let's, before we apply our rule here, just watch what happens when I sort A to Z. Remember, it's supposed to bring the smallest on top. So boop, I clicked it. Is the smallest one on top? Well, I can already see 0.08, 0.07, 0.02. That's the smallest. The reason why is the act of sorting, click, is another thing that triggers the rand function. So when you sort, it actually does sort the smallest number to the top and the associated records just for a second. But when it stops, it re-triggers it again. So when we click A to Z, even though the smallest number is not necessarily at the top, the data set was sorted using a uniform distribution. So here's our rule. Add the rand, click Sort A to Z button 5 times. It could be any number, 1, 2, 10. Just always be consistent, and then copy and paste the top 3 records. So you ready? Click in a single cell, 1, 2, 3, 4, 5, and that's it. The top 3, I'm going to Control C and paste over here. Now I can calculate Xbar for this particular sample equals average. And there we go. Control Enter. 215. So Xbar 215. Let's go see if we can find that over here. It's Su Jo Chin. So, oh my heavens, it's the very first one. Look at that. And there it is, that particular 215. Now if we go back to the sheet, Simple Random Sample, I built something off to the side here. And if you hit the F9 key, this is randomly pulling samples using a formula. But what I want you to notice is this value here can only be one of the Xbars that's listed here. And since we're using the rand function using a uniform distribution, it meets the exact definition for a simple random sample. Now in this video, we talked about a simple random sample using the rand function. We also saw how to list every single possible sample, calculate the Xbar, and then talk about the definition of a simple random sample. And we talked a lot about the sampling distribution of Xbar. And when we come back in our next video, we're going to start with this example. We're going to build a histogram. Notice some amazing characteristics about listing every single Xbar. That will lead us to the central limit theorem. And then that will lead us to confidence intervals and hypothesis testing, which is Chapter 8 and Chapter 9, and sort of like the culmination of everything we've learned in the class so far in 2 amazing statistical techniques, confidence intervals and hypothesis testing. All right, we'll see you next video.